and he's going to tell us about cuspidal curves in Pn, partition arithmetic, and lattice points in polytopes. Please, Ethan.
I'd just like to thank the organizers for giving me the opportunity to speak today. It's almost my 10th Brazilian birthday, so in a way, there are lots of sort of interesting patterns of numbers that are taking place both, I don't know, on the math side and sort of personally, so I'm happy to speak to you guys. Everything that I'm going to say here is pretty elementary, but there is at least some kind of bearing between what I'm saying, what I'm going to explain here, and what Pedro was talking about in the previous talk, in that Schubert varieties or generalizations of Schubert varieties are going to appear. I want to start by way of motivation. So in algebraic geometry, often we probe the geometry of a space by looking at spaces of maps either into or out of the space. A very classical paradigm is the case of holomorphic maps from P1 to Pn. And those are parameterized, so the parameter space of those maps is a Grassmannian, because every holomorphic map of fixed degree is given by a vector subspace of holomorphic sections. So we have holomorphic maps of degree D are encoded by linear series. Which are parameterized by these inclusions. Where LD is some line bundle of degree D. In fact, in this case where the variety is P1, it's just OD. So in a sense, those maps aren't particularly interesting, but they become more interesting if we start adding decorations. So for example, we could require that we only look at maps whose images have arithmetic genus G. And when n is equal to 2, those spaces are very classical. They're what are known as Severi varieties of plane curves. So we can start asking questions about Severi varieties now of curves that are no longer in P2, but are in higher dimensional spaces. And for example, we can ask whether these spaces M, N, DG are irreducible or not, sort of the first topological question. So why do I mention irreducibility? Well, for one thing, if we look at Severi varieties of plane curves, those spaces are always irreducible. And that comes from sort of famous work from Joe Harris in the 1980s on the Severi problem. So what we know is that Severi varieties of plane curves are always the closures of maps of a very particular type. So what we know is that in the case of M2DG, this is equal to the closure of maps from P1 to P2 with G simple double points in their images. In other words, I allow my images to look like this. And there are G of these. Okay, and actually, when we now relax this dimension 2 to be any dimension at least 2, it's going to be important to keep in mind the distinguished subvariety of maps whose images have G nodes. And in fact, whenever n is at least 3, it's going to turn out that the Severi varieties are not irreducible most of the time. And I'm going to try to give you some idea as to why that would be the case. And to do that, well, not very surprisingly, we're trying to do dimension counting for maps with singularities in their images. And in fact, instead of looking at maps whose images have nodes, we're going to focus in on special maps whose images have exactly one, in general, pretty bad cusp, or that is to say, a unibranch singularity in their images. Okay? So please, if anything isn't clear, stop me. Yeah, and in fact, I guess in this last sentence, there's this word value semigroup that shows up. So the value semigroup is, of a cusp is some way of quantifying this thing, which I'm going to review in a second. But it's some artifact, it's some topological artifact of this cusp. Okay, so what's a value semigroup? The idea is that if we fix a pointed map where we single out a cusp in the image and its preimage in the domain, then you can sort of locally uniformize this curve by a map of algebras, right? In sort of the usual contravariant way. So a cusp is described by a map of algebras. And in fact, I wrote C double brackets xi's, but this should really just be a polynomial algebra. And then the idea is that we look locally at a cusp. Cusp is parametrized by some n tuple of power series. So we just send xi to some power series in T. Okay, and then and so that describes the cusp locally. And in particular, the local algebra of the cusp is just it's just whatever is generated by these images. So is the algebra generated by phi1 up to phi n as an algebra, so multiplicatively. But then what's interesting is that on this power series ring, there's a natural non-Archimedean valuation that just sends a power series to its order of vanishing. So this is order of vanishing map in T equals 0. And the image of this composition is a semigroup of natural numbers, essentially because orders of vanishing in products are additive. Okay, so the image of this composition is what I call the value semigroup of the cusp, or of this pair consisting of a map and the preimage of the cusp. And here the philosophy is that whatever this parameter space of unicuspidal rational curves of a given degree with a cusp of given value semigroup is, whatever this M, D, comma, S actually is, somehow its topology should be controlled by S itself. Okay, so those are these spaces M and D, S inside of M, N, D, G, inside of spaces of maps of ambient dimension N and degree D. These are the objects that I'm going to be concerned with. And I want to give some kind of heuristic for how to estimate their dimensions. In order to do that, I first have to remind you that of a couple of standard facts about semigroups, and specifically how semigroups of cusps allow you to recover some of the geometry of the cusp. So basic fact is that any one of these value semigroups has finite complement in the natural numbers. So the number of elements of the complement is exactly the contribution to the arithmetic genus of the singular curve. So it's what I'm calling the genus of the cusp. And so it makes sense to study numerical semigroups, or in other words, semigroups, subsemigroups of the natural numbers with finite complements of genus G, for example. And now the idea is that imposing that maps have cusps of particular value semigroup S, that's going to impose conditions on the coefficients of the maps from P1 to Pn, these maps phi, right? Because again, any one of these phi is going to be singled out by a vector subspace of sections, phi of, let's say, t comma u up to phi 0 up to phi n. These are just homogeneous polynomials of degree d on P1. And our singularities are going to impose conditions on their coefficients. OK, and for the heuristic now, I'm going to go back to the space of maps whose images have G nodes and just tell you, so hopefully this sounds credible, the codimension of that G nodal sublocus is always n minus 2 times G. And the reason is that if you fix a choice of cusp, well, it's easy to work out in coordinates using sort of very, very naive linear algebra that that node imposes 2n conditions if you fix the preimage and the support of the node in the target. So you have 2n conditions. You cut down by n conditions corresponding to moving the choice of the support in the target, and an additional 2 conditions corresponding to the preimages of the node. And that means that each node imposes n minus 2 conditions on maps of degree d. And it's also not hard to show that the conditions imposed by individual nodes are additive. So in total, we get n minus 2 times g conditions. OK, so if it were the case that the Severi variety of maps from P1 to Pn with images of arithmetic genus G were actually contained in the closure of the G nodal locus, then it would necessarily have to be true that the codimension of that space inside of, when I say codimension, actually what I mean is this codimension inside the space of all maps from P1 to Pn of degree d. If it were the case that MNDG were in the closure of the G nodal locus, then it would necessarily have to be the case that its codimension would be at least the codimension of the G nodal locus, right? And we're going to show that that's not true. OK, so how are we going to do that? Well, I guess what I'm going to say is we have kind of a strategy for how this should go in general. But I want to sort of implement this strategy in two particular cases associated with two distinct families of value semigroups.
Sorry, I'm confused. Didn't you say that MNDG was irreducible?
Only when n is 2. So this is now the situation where n is at least 3. Yeah. Thanks. OK, so I want to try to implement a general strategy for estimating codimensions as sort of proof of concept in two distinct cases. So what are the arithmetically distinguished classes of semigroups that I'm going to focus on? The first one is just going to be what are called hyperelliptic semigroups. The reason why they're called hyperelliptic semigroups is that classically they're associated with hyperelliptic Weierstrass points on curves. But from a combinatorial point of view, it just means that we require 2 to belong to the semigroup. So if the genus of the semigroup is G, then that forces a set of minimal generators for the semigroup to be 2 and there, 2G plus 1. Okay, so that's one class of semigroup. Arithmetically, it's relatively simple, which is why I'm singling it out. Another relatively simple class of semigroups, but which has a very different arithmetic profile somehow, are what are called supersymmetric semigroups. So what's a supersymmetric semigroup? It's associated to, in order to produce one, you take n pairwise relatively prime positive integers, and then you just form products where sequentially you just omit one of the AIs in forming the product. So in that way, you produce a supersymmetric n-tuple of numbers, which minimally generates what I'll call a supersymmetric semigroup. Oh, and actually, it might seem just sort of random why I'm producing these two distinct types of semigroups. But again, I'll try to be more precise about this towards the end. The idea is that there actually is some good arithmetic reason why you would single out these two. In some sense, they have the structures of factorizations of elements in either of these two situations is relatively explicit. You can really understand how any given element of the semigroup factors as a non-negative linear combination of minimal generators. Okay, so back to dimension counting. So how do I estimate numbers of conditions imposed by cusps on morphisms from P1 to Pn if I fix a particular choice of value semigroup? So to do that, it's useful to distinguish between two types of conditions. And sort of the simplest conditions are what I'll call ramification conditions. And those are associated to vanishings of derivatives. So, namely, what do? We look at the vanishing orders of sections in the preimage of our cusp. Let's call the resulting numbers A0 through AN. And then what we do is we look at sort of the difference between that sequence of numbers and the sequence of numbers between 0 and n. So for ramification, I can associate in the preimage of the cusp what I'll call the ramification type of the morphism. So that is just the vector k that I get by taking the difference between A0 up to AN and then subtracting the generic sequence. Okay, and now we see the connection with the previous talk, because the idea is that if I look at the subvariety of maps where I fix, let's say I not only fix the value semigroup, but I also fix the ramification type in the preimage of the cusp, well then this subvariety of maps is actually a generalization of a Schubert variety, right? Because actually, so how does the Schubert variety arise in this context? Schubert variety would be associated to a generic cusp, where you don't have any sort of unexpected conditions on the coefficients aside from those imposed by ramification. Okay? So in some sense, the spaces, so these spaces, Mn, ds, whatever they are paved by generalizations of Schubert varieties. And it's actually these that I'm going to focus on for the duration. And actually, it's these conditions beside or beyond ramification that arise from the additive structure of the semigroup, or equivalently from the multiplicative structure of the local algebra of the cusp, that are going to be a bit more subtle, and where the combinatorics is actually going to be quite interesting, I think. And I'll try to give you a combinatorial model that, at least conjecturally and provably in the two particular situations that I described for you before, namely there's a hyperelliptic situation, there's a supersymmetric situation, I'll give you a combinatorial model that should account for these, in particular, should account for these conditions beyond ramification. in order to do that, I have to tell you a little bit more about combinatorics associated with numerical semigroups, so in other words, semigroups with finite, sub-semigroups of natural numbers with finite complements. So I think this relationship between Dyck paths and semigroups, which I'll describe for you now, this is actually something that I learned from another speaker in the conference, Maria Bras Amoros. I hope I'm not butchering her name. But I learned this from one of her papers. So the idea is very simple but powerful. Associated to any numerical semigroup, you can associate a Dyck path, or in other words, a lattice path in Z2 that starts at the origin and ends at G comma G, where G is the genus of the semigroup. So how does this work? Well, the idea is simply that if you imagine traversing the numbers between 0 and 2 times G, the idea is that anytime you encounter a number that belongs to the semigroup, you go to the right, whereas anytime you encounter an element of the complement of the semigroup, you go up, every time with a segment of unit length. And so then, very roughly speaking, the idea now is going to be that in my combinatorial model, ramification conditions are going to show up as Young tableau boxes underneath the lattice path, whereas conditions beyond ramification are going to be encoded as collections of boxes above the path. So I'll try to give a visual example to explain what that means. Actually, there's a typo in here. This gamma is a parameter that should no longer appear. So if you look at the semigroup 2, 15, it's a hyperelliptic semigroup. I'm going to assume that n is equal to 4, and that actually there's this other caveat, which is that the degree has to be sufficiently large relative to the genus that I should also mention. In practice, D probably just has to be at least 2G minus 2. But yeah, so in this particular situation, the space M4DS of maps from P1 to P4 with value semigroup 2, 15, that space will contain maps with various different types of ramification profiles in the preimage of the cusp. So let's pick one. Let's pick sequence, and actually I guess there's a difference in the convention. 2, 4, 6, 8 are just going to be the numbers A1 through A4. I'm omitting a 0 here. So the idea here is that to say that I look at maps with ramification profile 2, 4, 6, 8, it means that in the power series representation of the cusp, the power series have this particular form. I have t squared plus terms of, after an easy renormalization, f1 will be t squared plus terms of higher order, f2 will be t to the 4th plus terms of higher order, and so forth. And so graphically, in my representation of the semigroup and of the ramification of the semigroup, what do I have? Try to do the picture here. Actually, well, yeah. I don't know if I really want to reproduce this, but yeah. So G here is 7. So I have some 7 by 7 box. I have a 7 by 7 lattice square, and then the idea is that if you notice in this picture, I have I can distinguish this path um, 2, 4, 6, 8, 10, 12, 14. So actually the picture cuts off here. The idea is that this lattice path is my representation of the semigroup. And then why have I singled out these gray squares? Well, what you should think is that each one of the columns corresponds to an f sub I. So f1 is the first column, f2 is the second, and so forth. And then ramification is selected for by the gray boxes, which again are below the path that encodes my semigroup. And then what's less clear here is how these red boxes that account for conditions beyond ramification, how you produce those. And the scheme is as follows. So let's focus in. I'm just going to explain this first red box. I don't have red here, but. So how do I account for this red box? The idea is the following. Here, if you were to think generically, in the generic situation, you would expect that the vanishing order of, and here's what explains the convention. You would expect that the vanishing order of f1 squared minus f2, generically this vanishing order, so you notice that when you compute f1 squared, now it has the same leading term as f2. So you take the difference, and generically you would, because of that cancellation, you would expect that the vanishing order should be 5. The problem is that the 5 doesn't belong to the semigroup. So as a result, there's a condition on coefficients that's imposed exactly such that you're not in this generic situation. Okay, so in fact, when you move up this column, there's just some explicit inductive way of promoting these kinds of syzygetic polynomials to sort of iterated versions that produce additional conditions on higher order coefficients. And then if you now move from the second to the third column, for example, well, the first box will be associated to f1 to the third minus f3, this one to f1 to the fourth minus f4. And now you sort of start to see a pattern. And this also helps to explain why I've singled out this particular class of hyperelliptic semigroups, because these syzygies are particularly simple. And that, again, is just a reflection of the fact that the factorization structure of elements in the semigroup is simple. Numerologically, I want to just mention the fact that, so if you look at the sum of RP plus BP, ramification conditions plus conditions beyond ramification, you get exactly n minus 1 times g plus 1. And that's actually not a coincidence. So we show that in general, this phenomenon is true. What that means is that the codimension associated with this particular Severi variety with fixed ramification type 2468 is n minus 1 times g. And that's a general phenomenon, actually. OK, and then, yeah, this last sentence is just explaining, this is an explanation of each of the columns. OK, yeah, so, OK, so I don't want to dwell, because of time, I don't want to dwell too much on this. But in general, we have an explicit scheme of accounting for all algebraically independent conditions imposed by hyperelliptic cusps, which again involves sort of walking up a column and inductively producing more and more conditions. Another sort of outcome of our analysis is that anytime we look at hyperelliptic cusps and we fix ramification type, in every instance that we can observe, and in particular in this generic situation where the ramification profile is just a sequence of even, successive even numbers, those generalized Schubert varieties are irreducible and unirational. So it's kind of natural to wonder in what generality that phenomenon persists to. And that's kind of a direct, that unirationality is actually a direct outcome of of our explicit encoding of these algebraic conditions. Okay, so in the time that's remaining, I want to say something about how dimension counting should work in general, and this will also hopefully get to the supersymmetric case and also connection with lattice point counting for polytopes. So in general, what we're going to do is we're going to try to compute a codimension for Mn, D, S, and K, where we fix the ramification type. And the recipe is going to be prescribed by the following ingredients. So we need a presentation of our, so we start with a representation of our semigroup in terms of minimal generators. And then you notice this function rho, this arithmetic function that just computes for a given number S in the semigroup, it computes the number of elements strictly greater than S in the complement of the semigroup. So that arithmetic function rho is one ingredient. Another one is what are known as Betty elements that are sort of the primitive elements that determine the factorization structure, that completely determine the factorization structure of arbitrary elements in the numerical semigroup. So how are these things defined? The way you should think about them as elements that have at least two qualitatively distinct factorizations. How do you make that precise? Well, one way is the following. So if you fix an element of the semigroup and you look at its set of factorizations, you can associate a graph of factorizations whose vertices are indexed by the factorizations, and where the vertices in the graph are linked whenever the dot products of the vectors that describe the factorizations are non-zero. So an element is a Betty element anytime its associated factorization graph is disconnected. In general, what we expect is the following. So if we take a set of Betty elements associated to a given choice of value semigroup and also ramification type K, and we look at, so what this means is that we have to look for factorizations in terms of the union of minimal generators in S together with elements of K. And we collect all, and we look at all Betty elements that are less than the conductor of the semigroup. So the conductor is the number for which it's one, by definition, it's one more than the largest element in the complement of the semigroup. And now, oh yeah, I guess there's an additional ingredient. So there's some kind of linear algebra, there's some kind of linear algebraic input in addition that goes into this codimension formula. So if we single out a Betty element B, and we look at a set of representatives of all the equivalence classes where you, so for the equivalence class, I'm going to say that two factorizations are equivalent if there's a chain sort of vectors linking those two for which every two successive vectors have non-zero dot product. If we now take a full set of representatives of equivalence classes of a given Betty element, we form some kind of matrix. And then, well, we have to compute jumps in matrix ranks. Here V1 is just an arbitrary sort of reference vector. And then we have to compute its rank. And then we have to assemble all of those MBIs together and compute successive jumps in ranks. And then, so the idea is that this phi of B, or B sub I, is again some kind of arithmetic function. And then, roughly speaking, the idea is that, so for this codimension, in this formula, the sum of the ki's minus i's minus 1 comes from ramification. Then, for conditions beyond ramification, so here's where the content is. It's in this. We have to compute a sum over So B star is Betty elements for which phi is at least 1. And then for each of those elements, we have to compute the number of elements in the complement strictly greater than B times rho of B, which is this linear algebraic input. And then there's some kind of correction where these SI stars in C come from minimal generators that don't belong to the ramification vector. So I don't want to go into that. OK, so that's the conjecture in general. I see. So here, actually, the color didn't show up. In this picture, these two are supposed to show up as dark red, and they actually don't contribute because it turns out because this element 2g minus 4 gamma plus 1 doesn't belong to the ramification vector. But what's happening in this picture is that these columns where red boxes show up are exactly 4, 8, and 20, and those are exactly the Betty elements of the semigroup. So that's the most important takeaway from this picture. And then, yeah, maybe just to finish, I'm out of time. But we used this type of analysis to produce new families of Severi varieties for which the codimension is strictly less than the codimension of the G-nodal locus. And there's more than one way to do this, but we have examples arising from sort of generic cusps. So we have a couple types of examples. One is of generic cusps with ramification profiles that are successive sequences of even numbers. And because they're generic cusps, the idea is that in this situation, you only have ramification conditions. You don't have any conditions beyond ramification. So you just have to control the genus of a generic cusp. And we get some amount of control on that genus by showing that the elements of the complement contain at least this set of numbers. And that's enough to force the codimension to be strictly less than n minus 2 times g, at least with some additional numerical hypotheses. And then we have to work a bit harder. We could also do this in the n equals 3 case more recently. And in fact, we can show that the Severi variety associated with a generic cusp with ramification profile, any 3-tuple of consecutive even numbers. All right, so that is almost always of codimension strictly less than G. And in fact, we can also do the same thing in supersymmetric cases. So if we take a supersymmetric semigroup and a supersymmetric ramification profile, then it turns out that the associated Severi varieties are almost always of codimension strictly less than n minus 2g, provided the AIs satisfy a certain, provided they're sufficiently close together in a way that I won't make precise. But just to point out one last thing, to give the connection with lattice point counts for polytopes. So if you work out the codimension formula in this particular situation, it turns out again to depend on this ingredient rho of ABC, which is actually the unique Betty element of the supersymmetric semigroup generated by AB, AC, and BC. And you can relate this number rho of ABC to a lattice point count. So more precisely, what is it? It actually is just the number of integral lattice points in a simplex. And why is it this particular simplex? Because the idea is that, so if you multiply through these rational numbers by ABC, what you end up with is the point is that what you end up with is, for example, ABC minus AB minus AC minus BC. And what you're doing is you're computing factorizations of elements in the semigroup that are less than or equal to this number ABC minus AB minus AC minus BC. And what's nice is that it's sort of known in general that you can approximate discrete volumes of lattice simplices by their actual Euclidean volumes, which are these numbers, which are these polynomials, where I've just ignored the fractional pieces in these expressions. Maybe just to conclude, we would like to know, in general, if these generalized Schubert varieties given by fixing the ramification types are unirational, for example. Going forward, it would also be interesting to know if there's an intrinsic way, sort of free of coordinates, of either MNDGS or MNDGSK as a degeneracy locus for a map of bundles. If you could do that, then you could produce all sorts of more general Brunner type results for linear series on general curves of arbitrary genus, I think. And then finally, you can ask about extensions to cases where you allow the singularities to have multiple branches. So I apologize for going over time.